Hi, in this video, I'm going to introduce you to two types of functions and two types of circuits that hopefully should get you started on understanding how resistor-capacitor circuits, RC, and resistor-inductor circuits, RL, operate, function, and how they work mathematically. So, to get started here, first off, there's two functions that you're going to be seeing popping up a lot in this topic of physics or electronics. These two functions are kind of variations of the same thing. In fact, this function right here, if you have a keen eye or you just happen to really like differentiating things for some reason, you'll note that this function here is effectively the first derivative with respect to x of this function over here to the left. And we're going to get that in a future video here when we go over some derivations. But the thing that I want to highlight on these functions is a couple of things. First off, we should note that because they're exponential, they are asymptotic in this case. They're negative exponentials. And so for this first function here, it starts off at like a really rapid rate and gradually tapers off to a maximum asymptote that we're calling A here. Or we'll call that like the amplitude, the maximum value. Over here, it starts off at that maximum value as opposed to 0, and again, gradually tapers off to an asymptote of 0 at some point to x equals infinity. The other thing to note is a very unique quantity within these functions, which is what happens when x equals 1 here. Which, if you were to plug this in and just run it through your calculator, you would find that at x equals 1, this function will equal about 63% of its maximum value. Or, in other words, if you were to put this directly into your calculator, it would be about 0.63 times the maximum value. Over here, if you do the exact same thing, which I will do, at x equals 1, this function will be at about here, give or take, which is at 37% of the maximum value. Now, you're looking at these quantities and you're thinking, big whoop, that's really important. But I will very much emphasize the importance of understanding these functions and how they work later when we start delving into kind of the math behind what happens while we're in the process of charging or discharging the devices that are covered on this document. So, the other thing I want to do in this video is just introduce you to these two types of circuits and how they behave. So, first things first, RC circuits. You might have seen these already. They're very fun to play around with. But these resistor-capacitor circuits, as we call them, generally operate with, well, a resistor and a capacitor. But more specifically, generally you hook them up in parallel or something so that you can kind of switch it on and off. And this is the type of circuit that you would see if you ever had a little observation with like some electronic toy or computer that you've had, where when you switch it off, there's like a little light bulb that just doesn't seem to go out immediately. It like kind of gradually fades out. What's happening there is the work of a capacitor. And generally, these things are installed to kind of keep things going for just a little while longer in case there's just like a short temporary outage of power. So what's going to happen here is that when we hook the switch to A, like we have right here, well, this power source, this electromotive force, is going to push electrons around the circuit. Keep in mind, it'll be going in the opposite direction. But it's going to be pushing current, let's say, through the circuit, and charges are going to start building up along this capacitor. On this side of the capacitor, it'll build positive charge. On this side of the capacitor, it'll build negative charge. Okay. As that's happening, because there's this increasing amount of potential that's opposing our power source here, you're reaching a point where like the charges like that are in this path along the way aren't really going to know what to do at that point. Because if there was no potential over here, they would have tons of motivation to complete the circuit all the way through. But with this capacitor suddenly pushing back, like it's like a border checkpoint or something, the electrons are reaching this and they're getting stopped, and the capacitor's like, whoa, 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 hey, you should go back the other way. And maybe the charges will go all the way back and they'll hit this power source again, and that power source will be like, whoa, 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 hey, why are you coming back here? You should be going the other way. And the charges at that point are going to just kind of stop dead in their tracks. They will have no more potential. They'll have nowhere else to go because there's no energetic motivation to continue any further. So this capacitor, which builds up charge basically up to the potential that's provided to it, well, at that point, the current stops entirely. And so if we try that out on our little virtual circuit here, we'll show that, and we'll have a separate path here for electrons to go through. They have an alternate route. We want to be nice to the electrons. So when we do this, watch this. Keep in mind, charge is moving the other way because that's how charges move. Thanks, Benjamin Franklin. And notice, now in this branch containing the capacitor, that flow of charge has just completely cut off entirely. That's because, again, there's like nowhere else for this potential to go. In fact, if we were to get a voltmeter here and just kind of measure potential difference here versus the potential difference here, check that out. Total potential difference is 0. There's no place for these electrons to want to go, or at least they don't want to go there. If we check out the potential difference here, hey, now that's pretty nice. So, what we get with this is essentially a fully charged capacitor that now when we discharge, maybe we'll disconnect this voltage, we'll get rid of it. Suddenly those electrons do have motivation to start moving around. And once that capacitor runs out of its charge, it's exhausted its supply that it's built up, everything stops. But at a baseline, that's how capacitors and circuits work. And I want you to now rewind and check through either the first time I'm charging it, or I'll do it again here. And I want you to pay attention to these graphs as we do that. Those will be important to keep in mind for the next video. Alright. So notice that it's not really an instantaneous thing. It kind of tapers off, and hopefully you're already starting to notice that those functions look a little familiar. But I'll now introduce you to the other type of circuit in this video, which is a resistor-inductor circuit. And yes, I know it's a bit of a silly choice to make that L, but I was already taken by current. And now we've got basically an exact copy of the circuit we had over here. It's just that now the capacitor has been replaced with, well, an inductor. And the big idea to keep in mind with an inductor is that you can kind of think of it like we've now added inertia to a circuit. What I mean by that is, if we go over here and I connect this circuit, I complete it, so charge will start moving. Watch what happens here. Okay, did you see that? I'll do it again. And notice this one cuts off entirely, no more capacitor. We'll try this again, and watch the light bulb as kind of a visual cue. Okay, so notice how it takes like a little bit of time. It's like a gradual process to build up the flow of charge to its maximum value. That's essentially what an inductor does. It takes a little bit of push for charges to move through. And physically what's happening there is, well, if you've been following along with electromagnetism or anything of the sort. When you have moving charges through here, those moving charges are generating magnetic fields kind of along this direction here, like that. Oh. And now those magnetic field lines are interacting with these charges over here, just all along this circuit, and they're suddenly resisting the motion of those electrons trying to move into that real estate. Meaning that like the inductor is kind of resisting itself in a way. It takes a little bit of time for that magnetic field to fade away. You've kind of introduced this arbitrary flux to the circuit. So that's why we like to think of it as inertia in a circuit. Again, it's you never can just instantaneously move a heavy object. It's kind of a gradual process to speed it up. That's exactly what's happening here. So, the end result of this, as opposed to current completely stopping dead in its tracks, is almost the exact opposite of capacitors. Right, with capacitors, we started out with current flowing fine and dandy, and as the capacitor charged, our current got gradually less and less and less, if you were following those graphs here, until it reached 0. With an inductor, if we charge it, watch the current over here. Our current starts pretty low and then gradually approaches the value that it wants to be at after the inductor has stopped providing resistance to the circuit. So that is the primary difference between capacitors and inductors and how they work. And I'll be providing links to the PhET simulations so that you can try these circuits out for yourself and just kind of play around with them a little bit. But in the next video, I'm going to introduce you to some of the math behind these circuits and some of the important quantities that we use to analyze them a little bit. All right, so with that, I will see you in the next video. Thank you for joining me.